Welcome to Ask and Learn.
All right, so this problem asks us to suppose that a population grows according to a logistic model with carrying capacity 6,000 and K equals 0.0015 per year. So part A, they want you to write a logistic differential equation for this data. Well, this over here is our general form of this differential equation. Right? Well, we have that K is 0.0015 and M, which is the carrying capacity, is 6,000. So this is how we can write this model here using the logistic differential equation. So there we go. Part B now wants us to draw a direction field. So you can do this by hand, or you can do it using the computer algebra system. I use the computer algebra system. So basically, all of these lines are telling you that if you had a point at any one of these points, that the way the vector is pointing is the direction that the curve would have to go. So you can see here that at 6,000, because we have basically a flat line here at 6,000, we see that we have an equilibrium point here, meaning that once the population hits 6,000, it's going to stay at 6,000. So if we start anywhere below 6,000, our function will increase until it hits up to 6,000. So it'll taper off as it gets close to 6,000. And if we start anywhere above 6,000, our population will decrease and once again taper off and converge to 6,000. We also see here that our population, which is the vertical value here, does not depend on t, meaning that if you pick any height, any population, and you look all the way across, well, all of those directions are pointing in the same direction. So if you move horizontally, that won't affect the direction here on the direction graph. All right, part C asked us to draw curves on this direction field for initial populations of 1,000, 2,000, 4,000, and 8,000. So the one in red is with the initial population 1,000, and we can see here that the solution is concave up for a little bit, which means that our population is increasing at an increasing rate. And then around about 1,000 for t, about right here, we see that we have an inflection point. And then our solution looks concave down after that. So our population is still increasing, but at a decreasing rate, which makes sense because we need the population to taper off at 6,000. At 2,000, it's concave up for a very short period of time and switches to concave down, once again to taper off as we get near 6,000. If we start with a population of 4,000, you can see that we're concave down everywhere, which means our population will increase at a decreasing rate. If you look at 8,000, over here you see that we are concave up everywhere. So our population is decreasing because we need to taper off at 6,000, but it's decreasing slowly. It gets pretty steady and tapers off at 6,000 here. So these inflection points that we saw mainly with the initial population of 1,000 is when our population changes from increasing at an increasing rate to increasing at a decreasing rate. All right, now part D asked us to use Euler's method so that you could program a calculator or computer to use Euler's method with step size h equals 1 to estimate the population after 50 years if the initial population is 1,000. So this formula over here is from section 9.2, I believe, and this is Euler's method in general. So if we have a differential equation, that's this y prime equals f of x. Where they have x, we used t in this problem, and where they have y, we used p. And so this is our initial condition right here, and this is how we're going to define our x's as we keep going up. So for each value of x, we add the step size to it. In our case, that'll be 1, and that gives us our new x value. And so we get our new y value, yn is, well, we take the previous y value and add to it the step size, so 1 in our case, times f of the previous point. So I have here some pseudocode for us, so whether you want to do this on a computer or your calculator, this is the general outline. So your first step, well, we need to define our function, and that's going to be our logistic model that we did in part A. So you already know how to get this equation here. Our second step, now we need to input our initial start time and our initial population. So we wanted to start with the population of 1,000, so we have P0 equals 1,000 here, and we're starting that at time 0. Next, we have to input our step size, so that's h equals 1, and this n equals 50 here tells us that we're going to do this, we're going to do 50 steps, which makes sense because we need to get from year 0 to year 50 to figure out what the population is after 50 years. All right, so part 4 here is really important, and it's where we actually execute Euler's method. So we're going to do a for loop, and we're going to do this 50 times, so from 1 to 50. So the first part of this loop is, well, we need to figure out what f of t0 and p0 is, and I'm just going to call that a. Well, then we can see our next population, well, approximate our next population with Euler's method in part B here. And so we're going to take our initial population and add to it our step size times, well, what we found in part A here. Then we're going to increase our time. So we're going to say T1 is the time we started off with, plus our step size, which is 1 in our case. D here, the reason we want to print the new time and the new population is so we can keep track of each step of the process here. And then parts E and F here are redefining T0 and P0 so that we can do this loop again and again until we do it 50 times. And at the end of the day, we need to end this program. So if you run this, you're going to see that after 50 steps, which means 50 years, the population, well, this is going to spit out 1064.039, on and on and on. But we're talking about population here, so we want to talk about whole numbers. It doesn't make sense to talk about 0.039 of a person. So we'll actually say this gives us roughly 1064 as our answer here for using Euler's method. All right, so now part E wants us to actually find a solution here if we have an initial population of 1,000. So that is what we're doing here. This is our initial population, or sorry, this is our solution to this differential equation, and that comes from this section in the book. And so M, once again, our carrying capacity is going to be 6,000, and this depends on this A here. Well, A is going to be our carrying capacity minus our initial population, all divided by our initial population. So moving over here, we can compute that within the framework of this problem. So carrying capacity, this here is our M, and then here is our P0, that's 1,000, and A ends up just being 5. So this here is our solution. It's a population function. So we get P of t equals 6,000 over 1 plus 5 times e to the negative 0.0015t. And this part of the question also asked us to figure out what the population would be after 50 years using this function. So you can use your calculator here, and you'll see that once again we get roughly 1,064, which means that Euler's method was pretty accurate. All right, so finally, part F wants us to actually graph this function that we just found. And so this here on the left-hand side there, that is our graph, this one over here, of this function, P of t, that we found in part E. And so it also tapers off at 6,000. That's what this line is here. And you can see it has an inflection point roughly here where we go from concave up. So the population is increasing at an increasing rate to concave down. So our function is still increasing, but at a decreasing rate because our population is going to taper off at 6,000, which was our carrying capacity. And the graph I have here on the right is the graph that we drew using our direction field. So the red line on the graph on the right was also with the initial condition 1000. And if we compare the red curve on the right to the red curve on the left, they look like they match up. So it all worked out.